Okay, let's finish up our discussion of device interfaces and drivers for Linux for memory mapped I/O. And we just got a demonstration showing device interfaces and an example program to read from a camera device interface and write out to flash with more or less processing between those two devices. And how that can cause us to become CPU bound, IO bound, memory bound, etc. And so let's just talk more generally now that we know a little bit about how to use some utilities and so forth to look at drivers and memory and CPU and so forth. The kernel modules loaded for driver interfaces like UVC video. And USB, by the way, is, I believe, a built-in driver. So that's why it looks a little confusing when we look at it with LS mod. We see the audio USB drivers, but we don't see the actual USB driver because it's built into the kernel. We talked about analog I/O and digital I/O, the embedded hardware view already, and we talked about how in software we view drivers as word-oriented drivers, or char drivers as they're actually called in Linux, since char refers to bytes, and bytes compose a word, I guess. So that's the reason. It's a historical kind of name. And then block drivers used for things like flash devices, SSD, disk drives, network interface cards, cameras where we need high rate I/O. And that these are memory mapped, and there is a third kind of driver called a stack driver, but we'll talk about that after we talk about the basic word at a time and block drivers. So I/O gets memory mapped somewhere between working memory down here, which traditionally is mapped between 0 and the top of memory, whatever that is. So here I've got 200,000 hex, and that would be 32 megabytes SRAM, which isn't much by today's standard. So I might have a lot more than that. If I go up to basically 8 Fs or 1 and 8 zeros, then that would be the 4 full gigabyte space for a 32-bit system. And so one of the things we know is that Raspberry Pi 4 can have more memory, can have 2, 4, or 8 gigabytes, so it's got to have more than 32-bit addressing. The Raspberry Pi 3B, however, only has 1 gigabyte of memory, so that would go up to basically a quarter of the way up this address space. And so if you do a lot of memory mapped work, you get better with hex numbers. But go ahead and cheat and use your programmer's calculator if you need to, because we won't do a lot of that in this course. But you would lay this out, and based on the sizes of devices, working memory normally between 0 and top of memory, whatever that is. And then we would have memory mapped I/O somewhere in the middle, and we would map that based on the kind of I/O bus we have, or internal kind of bus like AMBA bus, either the AMBA or PCI Express bus. And then normally we have things like flash, non-volatile memory up high. This again is by convention. There may be ways to map flash at different locations, but it's traditionally mapped high. That way we can have memory mapped I/O between these two must-have devices, our boot device, our boot ROM, and our working memory. And then we may have some empty space in here. And if we try to decode these addresses, we'll actually get an exception, often called a bus error. Perhaps you've seen that. So in other words, there's just nothing there at that address, nothing to respond. That address can't be decoded. So normally the board support package code will map devices at memory mapped I/O locations when it enumerates devices out that it finds out on the bus during boot. And normally we'll boot out of the boot image. Then typically we copy ourselves down to working memory and jump to ourselves, and then continue to execute out of working memory We use working memory for stack, for data segments, and for malloc heap memory. And we execute out of there. We interface to devices in memory mapped I/O, and then typically we just don't use this boot flash anymore. We may have flash that we then map through a driver interface like the MMC block interface to set up a flash file system, but that would be independent of this boot ROM. Okay, so, and this was actually for VxWorks, as I recall, VxWorks system that I had where I actually wrote the board support package and set all this up. So these were real addresses and so forth. Within the working memory, then I would further refine address ranges for the use by the kernel, the Linux kernel, or in this case, this is a VxWorks kernel. And here I've got my debug pool, my interrupt service routine stack, my system code, system stack, boot ROM image, and boot ROM stack that I copied into RAM down from the non-volatile memory, boot parameters, interrupt vector table. The interrupt vector table is almost always at all zeros, so basically at the bottom of working memory. The idea there is that normally you use memory up here and you grow stacks down, so you're unlikely to wipe out your interrupt vector table. And so that's another convention. There's a lot of conventions with memory mapping, memory mapped I/O, mapping segments in memory. You can use virtual memory for embedded systems, but often they don't. They just use a simple memory management capability to do things like protect kernel code from writes. So they create some read-only memory segments. Another thing that we'll talk about here is the memory management unit can be used to set up some pages in memory through the memory management unit, so blocks of memory that are cacheable or not cacheable and those kind of things. Virtual memory is the idea that I've got a logical address that has to be mapped to a physical address, so that code uses only logical addresses rather than physical, and the MMU translates them. Whether that's used in an embedded system depends on whether you can benefit from virtual memory. Linux definitely sets up virtual memory, and it does so for a number of reasons. One is it actually can swap pages between memory and a storage device, and the other is that it uses it for memory protection, so to protect user space, processes from each other, to protect the kernel space from user space, code that's buggy, and so on and so forth. So that's fairly complicated. We don't go into detail on that in this course, but understanding a memory map and how it's used would be the first step toward also working to understand virtual memory and memory management units, which are normally available on all microprocessors that are designed to run a full operating system like Linux or even an RTOS that might have virtual memory support. Okay, so drivers, back to drivers. The last kind of driver we have is a stacked driver. So stacked drivers might be used for things like network stacks, TCP/IP, UDP/IP, flash file system or disk on chip, and file systems in general. Here I've shown a network stack with a TCP/IP stack and a sockets interface to an application, the OSI reference model, 7-layer reference model. So we might have twisted pair wiring, 802.3 gigabit Ethernet, IP and TCP running on that in basically kernel space, sockets API, interfacing us up to user space with a data presentation layer to our application. So drivers can be fairly complicated, like network stacks with some kernel modules as well as user space modules, or they can be built into the kernel, and or they can be pretty simple and just have device interfaces and an application layer interface. Here's a block driver. that you'll find on your Raspberry Pi or most any embedded Linux board that has NAND flash. So we have, as we said, word at a time drivers like serial, GPIO, relays, analog digital conversion interfaces might be word at a time. We have block I/O devices like the common flash interface or Ethernet link layer, and one of those block devices is MMC block on Linux. And then, of course, we just looked at stack drivers. So the MMC block is the block interface to the SD card NAND flash on Linux, which you'll find on your Raspberry Pi. Disk drivers like disk, spinning disk, or solid state disks normally are SCSI or ATA interface, which is very different from MMC block, which is more of a direct interface, the SD card interface, as you can see here. So you see the MMC 0 and the block interface set up on it, and we see there's MMC 0 detects a new high-speed SDHC card, and it gives an address, not quite sure how to interpret that address, of 0001, but in other words, we just have one SD card, and we're going to set up a block driver interface on it, and then we're going to mount the file system on it. So that's what this is all about. I got this from dmessage. So dmessage normally logs all the driver interface activity that occurs on boot with Linux. And driver design in general can be broken down into the application that interfaces to the driver, and then the actual module that lives in kernel space that really is executed when you call the driver through the system call interface, that in turn interfaces to a device interface down here. So normally this execution of this application interface is done in the application's context. And for example, I can make calls to the so-called standard entry points of open, close, read, write, create, and I/O control. Those cause me to call functions inside the application interface that are specific to the device that they interface to. So there's a lookup table that says, okay, you're calling open, the standard open. For the descriptor you gave, like dev video, I'm going to go to the UVC driver, and I'm going to call a UVC driver open that implements the specific device interface. And normally devices, you write into a ring buffer to write out to them. You don't really write, well, you do write to a camera. You can write commands to the camera to configure it. And so that might go through a ring buffer or directly. And as long as the camera is available for writing, I'm just going to go ahead and have the write succeed. If not, I'll either be told you need to try again later, or if this ring buffer is full, I might actually be blocked. So I can set up blocking or non-blocking semantics on the application interface. I can decide how many threads can access something at the same time. So does it make sense for multi-threaded access to the camera? What's the policy there? Normally it has to be opened. You decide as the driver developer how many different threads can open the camera at the same time, and it creates abstraction. When I read from the camera, for example, then either I get E again, or I get data, or I block, or I get a status, right? And I get the E again as typically as a status if I'm in a non-blocking mode. When I block, really what happens is the kernel module takes a semaphore on my behalf in kernel space, and it blocks until the semaphore is given by an interrupt service routine that unblocks my, in this case, kernel task, which is going to be the implementation of my user space process thread, which I know is kind of confusing, but that's the truth. And so Basically, device interfaces are always composed of specific code that interfaces to the hardware for writes and reads, or inbound DMAs and outbound DMAs, or both. Interrupts that are raised and interrupt service routines that handle those interrupts, and then semaphores that are given to the application interface. The device interface provides a hardware abstraction layer that can be tested without the application. So driver design is a nice approach that's used actually in RTOS as well as OSs like Linux. The VxWorks RTOS has the same driver framework actually as Linux. It's just not quite as fully featured perhaps. But you can actually load device interfaces as modules. You just don't have all the memory protection and virtual memory features that you have in Linux. So one thing to keep in mind with drivers is if you DMA, so in other words, you do direct memory access where you ask a device to push data into your memory, or you take data that you prepared and you want to push it out to the device, you have to make sure that the cache and the DMA are coherent. So there's some simple rules for this. So if you, and I've given the VxWorks calls here just because I'm familiar with those, because I've written VxWorks as well as Linux drivers, but they're kind of similar in Linux. If I have data that I prepare that needs to go outbound on an outbound DMA, I need to invalidate the cache. I need to flush the cache, prior to the DMA write initiation. And if I have data that comes in on an inbound DMA, I need to invalidate it if those memory locations are cacheable. So one of the things I want to do is basically determine whether my, and I'm going to write on my slide here, whether my DMA is inbound or outbound. So the issue is that I have memory here, right? Here's my memory. And I have a DMA that puts data into memory. And I have cache, and so here's my cache and here's my CPU, right? And I might have a line of memory that's here, and then that was also the one that I wrote to, right, with my inbound DMA. And so I've updated that here, and I need to sync that up to cache before I start processing that with my CPU. And so I need to invalidate. I need to have the CPU invalidate that when it gets the DMA completion, either via an interrupt or by polling a DMA completion queue. It needs to invalidate the memory location that was DMA'd before it starts to process it to pull it up into cache. And likewise, if I'm going to go the other way, so if I'm going to have this go out, I need to make sure that it gets flushed here. So I need to flush here before I start an outbound DMA over here. And so that's pretty simple. So I need to call cache flush prior to DMA. I said write or outbound, and I need to invalidate prior to DMA read or inbound DMA, right? And that's for cache coherency. Okay, so otherwise I'm going to read stale data. I also need to make sure that I/O data is aligned on cache line boundaries. So that's interesting. If I don't do that, then I'm going to have cache lines straddled by memory locations. I'm going to have to invalidate multiple lines or flush multiple lines, which could get complicated. By the way, this is a source of serious data corruption, and something that I've seen as a somewhat common error in new drivers. If you have problems with data corruption, what you can also do is just mark these memory regions as non-cacheable in your memory management unit. rather than worrying about invalidation and flush. So anyways, the great thing about the driver approach is that generally any inefficiency of writing a driver is outweighed by the software engineering value. Even the cyclic executives like the Texas Instruments board that I pointed out has driver abstraction, at least device interface abstractions like the Texas Instruments PDL. The full driver abstraction adds overhead and complexity, certainly, but it provides you protection, security, function calls for in a table for lookup, and you can use tricks that we'll see in this course and in the final course in the series to use zero copy buffering to avoid some of the overhead as well. So it's not all bad. And so in other words, the abstraction can be well worth it. What do you get out of abstraction? Well, portability, testability, a lot of the software engineering abilities, a single point of access and maintenance. You enforce multi-thread usage policies, separate buffering and ISR from use, common application entry points, and scheduled I/O. So in other words, do your data processing in your user space threads rather than kernel tasks or in the driver itself. As cyclic executive, you might do some of the processing. Obviously, it's all kernel space, but you want to do processing in your main loop rather than all in your interrupt service routine as well. So there's lots of driver writer resources out there for kernel modules loaded after boot, for built-in drivers loaded with the kernel image. We have a much newer Linux kernel now, but there's a good book out on Linux 2.6 device drivers by Rubini and Corbett. Jerry Cooperstein has updated Linux driver examples that I've noted in resources, and the Linux Foundation has some of the most current information on drivers. VxWorks drivers, I've written several drivers that I've made available to prior classes that I've taught at University of Colorado on this topic that you can look at. They're similar in nature to the Linux drivers. You still have a driver entry point registration table. There's a nice programmer's guide section on how to write VxWorks drivers. And so really the driver abstraction is useful for RTOS or for an OS. And so that covers our overview of drivers. Thank you very much.